All right, so today we are going to start talking about different type of numbers than what you've used before. Okay, so this is just a little handout that is going to talk about different types of numbers. So there are many different types of numbers that we put into different categories, some of which you've come up against before and some of which you haven't. So we're going to talk about some proper names for these and just what these different number systems are. Okay, now the first thing you're going to notice is that we've got this one box here, and it's sort of like kind of like those Russian nesting dolls, right? So the way that this is set up is that any number that is in this box is also in, say, this box here. So anything that's a natural or counting number is also a rational number. Okay, similarly, anything that's in this box is also in this box. So anything that's an integer is also a real number. Okay, so they kind of stack like that. Irrational numbers, right? Not the same thing as integers. They're separate, but both are real numbers because they're both in here. And then we got these imaginary numbers over here chilling out by themselves. Yeah, we're going to talk about imaginary numbers today. Okay, so now that we've kind of established that, let's talk about these different ones. So the smallest number set that we have is called the natural, either the natural numbers or the counting numbers. Okay, and that name makes sense because if I were to point at you, if you were sitting in class in front of me, and I were to point at you and I would say, hey, you, start counting, how would you do it? Right? Well, you would naturally start counting 1, 2, 3, 4, 5, right? And keep going until, you got bored or I told you to stop, right? That is what your natural numbers are. Okay, so natural numbers are just 1, 2, 3, and so on. Okay, so it's the natural things that people see when they think of numbers. Okay, now the next set that we have is the whole numbers. So the whole numbers include all of the natural counting numbers, okay, with one additional number, the number that looks like a whole, 0. Okay, so 0 is also a whole number. So when we talk about the natural numbers, 1, 2, 3, right? Whole numbers are 0, 1, 2, 3, and so on. Okay, the next set that we have is the integers, and this is where our friends, the negative numbers, come into play. So you should, in theory, know what the integers are, okay? But your integers are -1, -2, -3, and so on. But remember, anything that's in this box also includes anything inside the other boxes. So altogether, the integers are all of the positive and negative whole numbers, right? So positive numbers, negative numbers, and 0. All right. Next set that we have is called the rational numbers. And you're going to see the root word ratio in the word rational. These are numbers that can be written as fractions. Okay, so these are numbers that can be written as fractions. Okay, they don't necessarily have to be written as fractions, but they can be. Okay, so examples, 1/2 is a rational number. Okay, 11/5 is a rational number. Even though it's improper, that's fine. Okay, but like -0.3333 repeating, that's also a rational number because I can write that as a fraction. That's 1/3, right? So anything that, anytime you have a decimal that either stops, so something like, I don't know, 0.35827, right? That stops somewhere. So I could write that as a fraction. Or if it's a decimal that goes on forever but has some sort of a repeated pattern. So this one is obviously just threes over and over. Okay, or if we had something like 0.12121212, right, going on forever, that's got a pattern to it. So that would also, it's possible to write that as a fraction. We're not going to get into how, but it is possible. Okay, so rational numbers, anything that can be written as a fraction. And you'll notice that all of these numbers could also be written as a fraction, right? If you stick a 1 under it, it's a fraction. Okay, so those are all rationals. Okay, now we have rational numbers, and then over here we have this extra set called the irrational numbers. So rational numbers can be written as a fraction. Irrational numbers can't be written as a fraction. So these are ones that can't be written as a fraction. Okay, so anything that can't be written as a fraction, so numbers that you're familiar with that are irrational, the square root of 2. So any square roots where there's not an exact answer, like the square root of 9 is just exactly 3. Okay, anything that's not an exact answer is going to be irrational. Okay, if you were to throw this into your calculator and take a look at what the decimal is, it's a decimal that goes on forever, but there's no kind of pattern like there is with this guy. Okay, so that's an irrational number. Another example would be like pi, right? 3.1415926, blah, 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 right? It's a decimal that goes on forever with no repeated pattern. Okay, so those are, I think, are the most common examples that you're going to be aware of right now. But those are what your irrational numbers are. Okay, now real numbers don't add anything, they just join together these two sets. So numbers that can or can't be written as a fraction, those are included in the real numbers. Okay, so that's kind of what we're looking at here. So we've got real numbers in this box, and then over here we have imaginary numbers. And I know what you're thinking, Miss King, that sounds ridiculous. What is this imaginary number thing? Well, you're going to watch some videos on YouTube that are going to kind of talk to you a little bit about imaginary numbers. But basically, at some point in time, there was this guy, and he was trying to solve this problem. And he knew that there was an answer to the problem, but the method that he was using wasn't allowing him to get that answer. Okay, so like he had this problem, and he knew the answer was 3 because he could just look at it and plug the number 3 in and see that it was true. But he couldn't calculate the answer by like solving the equation. So because he kept running into this problem. And the problem that he kept running into was that somewhere in his solving process, he was running into the square root of -1. Okay, and the square root of -1 is not a thing. There are no numbers that when you multiply them by themselves, you end up with something negative, right? Because if you multiply a positive by itself, it's positive. If you multiply a negative by itself, it's negative. I'm sorry, it's positive. If you multiply a negative by itself, it's positive. Okay, so in order to get a negative answer, you have to have one of each, and that can't be a perfect square, right? So we can't take a square root of something that's a negative number. So this guy kept running into this problem of the square root of a -1 until eventually he just said, all right, forget it. I'm just going to pretend that this is an actual thing and keep going with my math and see what happens. And lo and behold, by doing that, he was able to find the answer that he was looking for. Okay, so imaginary numbers, it's this thing, it's not really a thing. There's really no such thing as an imaginary number. But by pretending that they exist, we can solve mathematics that we can't do without them. Okay, so that's why we call them imaginary numbers. Now you're going to see an argument in the video that they shouldn't be called imaginary numbers and that they really do exist. So you'll kind of see both sides of it, but that's where the idea of the name came from. All right, so that's what we're talking about with imaginary numbers. And square root of -1 is the big one, but the square root of negative anything, right? So the square root of -5 or the square root of -18, right? Those are all imaginary numbers because you can't take square roots of negatives. Great, so now that we've talked a little bit about this number system and kind of given you an idea of where these imaginaries come from, all right, we are going to talk about complex numbers. Okay, sorry, this video is going to be a bit of a long one. All right, so complex numbers. Okay, what these things are, complex numbers are numbers that can be written in the form a plus bi, where I is the imaginary unit. Unit meaning like 1. Like 1 is the unit for our number system. Okay, so it's the imaginary unit. So it's a plus bi. A and b have to be real numbers, right? So they're numbers that either can or can't be written as fractions. And then I is your imaginary unit. I is defined as the square root of specifically -1. Okay, that is the thing that you're going to have to just know cold. You shouldn't even need to think about it. You just need to know that I is the square root of -1. And similarly, you need to know that I squared is -1. Okay, because squaring and square rooting cancel. Okay, so you just need to make sure that you know these two things just flat out. Don't even need to think about it. You just know, oh, I squared -1. All right, great. So let's take a look at simplifying radicals. Right, so simplifying radicals when we have negatives, it's actually pretty simple. It's very similar to just simplifying radicals. So this guy right here, what I'm going to do is I'm going to break this into the square root of -1 times the square root of 4. Right, that's the thing you're allowed to do with radicals. Okay, and then I know that the square root of 4 is 2, and I know that the square root of -1 by definition is I. Right? So the square root of -4 is 2i. Oh, and you know what? I almost forgot. Oh no, okay. Sorry. I was going to throw in a positive or negative there, but you don't do that. Okay, so this is a question that comes up a lot. How come when we're solving and we take a square root, we need a positive or negative, but when we're just simplifying radicals, we don't? Okay, and the reason why is because it ties into the actual solving process. Okay, when you're solving something, you're starting from somewhere and you're trying to undo things that were done, right? And in trying to undo things, when you have a square to something that you're undoing, you don't know if they started with a positive or negative number. And that's why we have to include both answers. But here we're just simplifying and we're just assuming we start with what we start with. Sorry, brief tangent. Back to simplifying radicals. So this guy, similarly, that's the square root of -1 times the square root of 9. Well, the square root of 9 is 3. The square root of -1 is I, so it's 3I. Okay? Square root of -25, well, you know the square root of 25 is 5, and the square root of -1 is I. Okay, so you don't have to do this intermediate step. I'm just kind of showing you where it comes from. So then there we go. All right, square root of -12. So what I'm going to do is I'm going to simplify the square root of 12, and then I'm going to just pop an I in there, okay? So 2 ways of doing this. I don't care which one you do, whether you break this into the square root of 4 times the square root of 3 times technically the square root of -1, right? Or you could birthday cake it. I know the square root of 4 is 2. Square root of 3 doesn't simplify, and the I is going to go right here in the middle. Okay, so it's 2I root 3. All right, and then these last two, okay, the thing that you need to be aware of here is that squaring and square rooting cancel each other out. So when this simplifies, it's going to simplify to just -8. And similarly, this one will be -10. Okay, now the reason why I bothered to put this on here is because you got to be careful with these ones. That is the answer, okay? But what happens sometimes is people will say, okay, well, the square root of -8 squared means the square root of -8 times the square root of -8. And then they'll say, oh, well, -8 times -8 is 64. And then, oh, well, the square root of 64 is 8, right? Well, that's not true. That's not the right answer, okay? Squaring and square rooting cancel, and you're back to -8. So this is something you have to watch out for when you are dealing with simplifying radicals, all right? What you should have done if you'd had a problem like this, what you should have done was taken the i's out first, okay? So this part's wrong. So what you should have done is you should have made this I times the square root of 8 times I times the square root of 8, right? And that would have given me I squared times the square root of 64. And then from there, you'd say, oh, well, I squared is -1. We said you have to know that, right? So that's -1 times 8, and there's your -8, which is the right answer. Okay? So tons of extra work, right? Just know that that's the answer, but that's how you would handle a problem like that. Okay, great. So that's how you simplify radicals. So that's really not much that's new. You're pretty used to that. All right, so the next thing we're gonna look at is powers of I. So what our goal here is we're gonna look at expressions like this where you have I to some ridiculously high exponents, and you're gonna be able to look at that and quickly and easily figure out what is that equivalent to. Okay, and to do that, we're gonna kind of build a pattern here, okay? So follow along, bear with me as we do this. All right, so we're looking at powers of I. So we're starting out with the easy one, I to the first power, right? Anything to the first power is just itself. Okay, then I squared, we know by definition is -1. Okay, cool. So then when we need I to the third power, so I to the third power would be the same thing as if I multiplied I squared times I, right? If I multiply I squared times I, you add the exponents, that gives me I to the third, right? So if I know I squared was -1, and I know I is just itself, when I multiply that together, that's the same as -I. Great. All right. I to the fourth. I've got a couple of different options for how I could get I to the fourth, right? I could multiply I to the third times I to the first. But another way you could get to I to the fourth would be if I did I squared times I squared, right? That's the same as I to the fourth. And I know I squared is -1. And then this I squared is -1. And -1 times -1 is +1. Right? So that's just +1. Different from what we did here because here we had square roots. Here we don't have square roots. Okay? All right, cool. So then the next one that we're going to have, I to the fifth. Please note, I'm starting a new column. That's important. Make sure you start a new column also. All right, so I to the fifth. How do we get to I to the fifth? Well, the easiest way is to do I to the fourth times I, right? That's going to get me to I to the fifth. I to the fourth is 1. I is just itself. So 1 times I is just I. All right. I to the sixth. What's the easiest way? Well, I like this 4, right? I like that I to the fourth is 1. I'm going to stick with that. So for I to the sixth, I'm going to say that's the same as I to the fourth times I to the second, right? Add your exponents, it's I to the sixth. So this is the same as 1 times I squared, which was negative 1. Okay, so that must be negative 1. All right, I to the seventh. Again, I'm liking that this I to the fourth is one thing. So to get to I to the seventh, I'm going to use I to the fourth times I to the third. Right? Well, I to the fourth is 1 times I to the third. That's negative I. Okay, and then I to the eighth, right? Well, I to the eighth, that's the same as I to the fourth times I to the fourth, right? Which is 1 times 1, which is 1. You starting to notice something yet? Starting new column. That's important. Make sure you start a new column. I to the ninth. Well, if I know I to the eighth is 1, I'm going to use that fact to my advantage, right? So if I do I to the eighth times I to the first, that'll get me I to the ninth, right? 1 times I is I. Okay, I to the 10th. Again, I know this guy. That's very convenient. I to the eighth times I squared gets me I to the 10th. Well, 1 times negative 1 is negative 1. Okay, I to the 11th. Well, I've got 8, 9, 10, 11. So 1 times negative I is negative I. Okay, and then I to the 12th. Well, I could do I to the 8th times I to the 4th. That's just 1. Okay, so if you haven't picked up on it yet, you've got this little cycle going here, right? Where it's rotating between these 4 different things over and over and over. Okay, so there's this really nice pattern that you can do. So here's how I use this to my advantage. When I'm looking at simplifying some of these exponents, I'm thinking to myself this pattern right here. What I usually do is I write that exact pattern down on the side of my paper, and then I know that the bottom number, the 1, is always going to be anything that's a multiple of 4, and I can use that to figure out where anything else falls, right? So if I can find the multiple of 4 closest to whatever I'm looking for, then I can figure out what the rest of the pattern fits in. Okay, so let's look at some examples. So this one we got 5 times I squared. Well, I squared is negative 1. So this is the same as 5 times negative 1 or negative 5. Okay, this guy right here, 3I squared. Okay, well, I know that that's the same as 9I squared, right? And I know I squared is negative 1. So that's 9 times negative 1, negative 9. 2I to the third power, right? That's 2I times 2I times 2I. So 2 times 2 times 2 would give me 8, and then 3 i's, right? And I to the third power is negative 1. So this, I'm sorry, negative I, excuse me. So I to the third is the same thing as negative I. So this is the same thing as 8 times negative I, which is negative 8I. All right, this guy here, negative 3 to the fourth power. 4 negative 3's multiplied together is going to be a positive 81, I to the fourth. And I to the fourth is 1. So that's just 81 times 1, which is 81. All right, great. Well, that was convenient because all of them were written right here. But now we're getting up to some higher powers. So this one's I to the 23rd. I don't have that in my table yet. So here's how I'm going to think about this. I'm definitely not building out a whole table. That would take me forever. Okay, so here's how I'm thinking about this. So I'm looking for the closest multiple of 4 to 23. So 4, 8, 12, 16, 20, 24. 24 is a multiple of 4, right? So I know that my pattern, right? My pattern here is that I go I, negative 1, negative I, 1. So I know that I to the 24th as a multiple of 4 would be here, right? Which means that I to the 23rd would be right above it. So that is the same thing as negative I. Okay, so I gotta throw equal signs in there. There we go. That's less confusing. Okay, so this is the same thing as negative I, so that's 4 times negative I, or negative 4I. All right, next guy, we want I to the 82nd. So I'm looking for the closest multiple of 82. So closest multiple of 4 to 82. 80 and 84 are equally close. It doesn't matter which one you want to use, right? So if I started with, say, 80, right? Here's my pattern. It goes I, negative 1, negative I, 1. So I know I to the 80th would be here. So that means that for I to the 81st, I would start a new column and be back at the top. And that would put I to the 82nd here, right? So this would be I to the 81st, and then this would give me I to the 82nd. So this is the same thing as negative 1. So that's just negative 5. All right, this guy here, 48. Well, 48 is a multiple of 4. So that's a multiple of 4. It's got to be 1. So that guy's just negative 3, done. All right, and then this last one, 37. So closest multiple of 4 to 37. So 4, 8, 12, 16, 20, 24, 28, 32, 36, right? So 36, I to the 36th is going to be the bottom of my pattern. And I'm just filling in the rest of my pattern. So then I to the 37th would be up here. So that's just I. So this is simply 15I. Okay, so that's what you want to kind of use. Just as long as you got this pattern, and you don't have to memorize this, right? These two you had to know cold, right? You just need to know that I is I and that I squared is negative 1, right? Well, once you know that, to get I to the 3rd, you just multiply them together and it's negative I. And to get I to the 4th, you're doing I to the 2nd squared, right? So building this pattern is pretty easy to do. And once you have the pattern, figuring these out isn't so bad. All right, so that is the idea of imaginary numbers, complex numbers. I hope you enjoyed that YouTube video about complex and imaginary numbers. I think it's really interesting and you can learn a lot from it.